Hello, today we'll talk about the double pipe heat exchanger, which is one of the simplest type of heat exchangers. It's called a double pipe because one fluid flows inside a pipe and the other fluid flows between that pipe and another pipe that surrounds the first. In this double pipe heat exchanger, a hot process fluid flowing through the inner pipe transfers its heat to cooling water flowing in the other pipe. The system is in steady state until conditions change, such as flow rate or inlet temperature. There are two flow configurations in a double pipe heat exchanger: co-current and counter-current flows. The co-current is when the flow of the two streams is in the same directions. The counter-current is when the flow of the streams is in the opposite direction. There are many applications for double pipe heat exchangers. We mentioned some of them. The double pipe heat exchanger is a good fit for a true countercurrent flow, to which maximizes the temperature differences between the shell side and the tube side fluids, resulting in less surface area required for a given duty. Also, it's especially suitable for extreme temperature crossing, high pressure, high temperatures, and low to moderate surface area requirements. It uses a single pipe within a pipe design and are commonly used for high fouling services. In commercial aircraft, heat exchangers are used to take heat from the engine's oil system to heat cold fuel. This improves fuel efficiency as well as reduces the possibility of water entrapped in the fuel freezing in components.
In this simulation, you can see how the fluid of this double pipe heat exchanger is flowing. We can see how the hydraulic diameter holds the colder fluid, where the inside diameter holds the warmer fluid. This can help visualize the hydraulic diameter that can be used to calculate the fluid calculations. The equivalent diameter is a bit harder to visualize, but will only be used for heat transfer calculations.
Reynolds number depicts the fluid state either being laminar, transitional, or turbulent as shown on the left and right hand side of the screen. To maximize heat transfer, the system has to be in turbulent flow. Reynolds number is described by the equation shown on the screen, where rho is density, v is velocity, d is diameter, either effective or hydraulic, and mu is dynamic viscosity.
The objective in using a heat exchanger is to transfer as much heat as possible for a small cost if necessary. The graph below demonstrates the effect of the flow rate variation of the characteristics of a counterflow versus the parallel flow. Usually on a double pipe, the warmer fluid goes into the inner pipe and the cooler fluid goes into the outer pipe. Normally, counterflow is used to get the most heat transfer between fluids on a double pipe heat exchanger. If you want a smaller amount of heat transfer, then parallel flow will be used. To calculate the heat balance, you will need the mass flow, the heat capacity, and the temperature of both fluids, warm and cool. For an overall, you need the heat transfer coefficient, the area, and the log mean temperature.
The overall heat transfer coefficient represents the total resistance to heat transfer from one fluid to another. Assuming that the warmer fluid is in the inside pipe, the heat is first transferred from the hot fluid to the wall by convection, through the wall by conduction, and from the wall to the cold fluid again by convection. Any radiation effects are usually included in the convection heat transfer coefficients. The general equation to find the coefficient is displayed on the first bulletin, where Q is the heat transfer rate, A is the area, T subscript Lm is the log mean temperature difference, where in a heat exchanger, the log mean temperature difference is the appropriate average temperature difference that is used in heat transfer calculations, and it is also known as the driving force. Online modeling of commercial heat exchanger is done by tracking the overall heat transfer coefficient. The overall heat transfer coefficient tends to decline over time due to fouling. An analysis of a double pipe has been previously covered. The process is given in detail, and the link to the video can be found in the description.
Fouling. Fouling is the accumulation of unwanted materials on the walls and surfaces of the pipes inside the heat exchanger. It is detrimental to the function of the heat exchanger as it restricts heat transfer and fluid flow. Fouling in most applications is inevitable with time, and periodic maintenance and cleaning is important for efficient operations of the heat exchanger. There are different types of fouling mechanism. They can occur individually, but in most cases they occur simultaneously, like scaling and corrosion. Scaling is one of the most common types of fouling. It is the result of the insoluble minerals in fluid being deposited onto the pipe surfaces. Particular sediment comes from dirt, rust, and other foreign debris that goes into the unfiltered fluids and is deposited on the usually floor of the pipes of the heat exchanger. Chemical fouling is usually due to the fluid being heated to its temperature where it thermally decomposes. This degradation then is deposited onto the walls of the heat exchanger. Biological fouling is due to living organisms, microbes, algae blooms, even as big as zebra mussels and barnacles.